Hello students, in this video I will be talking about the topic of threaded binary trees. Okay, so the topic is threaded binary tree. Before I begin the topic, let me quickly recall what is a binary tree. What is a binary tree? A tree where a node called as parent node has has or can have up to two child nodes. It can have up to two child nodes. Okay. So let us now start with the topic of threaded binary trees. See, for example, if I take one binary tree, okay, let me write one binary tree. This is the binary tree. This is the binary tree. Okay. Now check the number of nodes in this tree. The number of nodes. The number of nodes, I'll call that number of nodes as n. See the number of nodes it has. So 1, 2, 3, 4, 5, and 6. The number of nodes are 6. Okay. And see the number of edges it is having. Edges it is having. Okay. Edges. Edges means those lines. So 1, 2, 3, 4, and 5. 5 lines it is having. 5 edges. So if I have to connect this if I have to connect these nodes and edges, how will you connect? How will you find the connection between them? Can you tell me? If the nodes are 6, the edges are 5. So how can I write with respect to each other? So I can say that if the number of nodes is 6 and the edges is 5, number of nodes are represented using n. So the number of edges is n minus 1. Correct? Number of edges is n minus 1. Okay. And also, what about the total number of links that are possible? Total number of links that are possible for this binary tree. So assume binary tree means we can have up to a maximum of 2 child nodes. So, so I can have 1 here, 2 this line. I'll draw the lines. Okay. So 1 is this, 2, 3, 4, 5, 6. Okay. So I can have at the most how many links I can have. Okay. I can have up to 2 times n number of links. 2 times n. How is this possible? 2 times n. Let me show you. Okay. So see. So 1, 2, 3, 4, 5. Okay. 6, 7, 8, 9, 10, 11, and 12. 12 links are possible. Correct. So it is 12. Okay. So if it is 12, with respect to the number of nodes, it is 2 times n. Correct? 2 times n. See, total number of edges that are available that I've drawn is 5, and total number of links that would have been possible is 12. So total number of unused edges, that means some I have not drawn only, right, in this particular tree. So unused edges, how many are there? So it is 12 minus 5, which is equal to 7. So 7 links I have not actually drawn in this tree. So how can I represent this with the help of the nodes? See, if the node is 6, The unused edges is 7, so it is n plus 1. N plus 1 edges I'm not used only. So if you consider a binary tree, these many edges were possible also, right? Other than the ones I've used. But these are going waste. I need to have it, but I'm not written it. Right? So what we can do is, okay, we can have some, you make some changes to your existing binary tree so that these unused edges or links can also be utilized in a way. Now, how to use this? Let me show you. Okay. See, I'll remove all those. This is also not. This is also not. So okay, let me draw it again. So it was like this. Okay. So let me show you the linked representation of this binary tree. If you have not watched it, kindly watch that video so that you can understand. So we are making use of linked list in order to represent a given binary tree. So the first one is A. So like this, A is a data part. Then two parts are linked part. So from the left, A's left child will be B like this. And A's right child is going to be C. Okay. Also, B's left child is going to be D. And B's right child is going to be E. And C's left child is going to be F. Correct? This is how you do the linked representation. And in this also, if I consider the unused edges, see the unused edges, if I consider, so this one was unused, right? Because it is not pointing. This is also unused. This is unused. This is unused. This edge is, this particular part is also unused. This and this. See, so many are unused. 7, right? So these are not pointing to anything, right? So what you can do in case of a threaded binary trees is, okay, if there are more number of null pointers than the actual pointers, these are null pointers. See the ones I've highlighted in orange, these are null pointers because they're not pointing at any valid location, right? So if there are more number of null pointers than the actual pointers, these null links that you see here are represented by a pointer called as threads. Okay. They are represented by a pointer called as thread, which points to the other nodes in the tree. So what we do is, instead of keeping this as empty, we connect it within the nodes in the tree so that it is not left empty. And those pointers that we use are called as threads. Are you understanding the concept? See, when if there are more number of if there are more number of null pointers, if there are more number of null pointers as compared to the actual pointers, as compared to the actual as compared to the actual pointers, then replace replace these null pointers, replace these null pointers with a pointer called as with the pointer called as threads. Okay. Now, how do we replace? That is the next thing. Okay. So, we will try to construct the threaded binary tree. Sorry. Let's construct the threaded binary tree. Construct threaded binary tree. Suppose there is a pointer called as PTR. Suppose there is a pointer called as PTR and it has, this is a PTR, okay, and its left child, if the PTR of left child, if the PTR of left child is empty, okay, then you have to with the replace it with the in order, you have to replace it with the in order successor. This point is very important. In order successor of PTR. In order successor. Okay. Likewise, if there is PTR of right child, if there is PTR of right child, and if that is empty, if the PTR of right child is empty, then replace it with the in order. Sorry, here there is a small correction that I want to make. If the left child is empty, then it should be the in order predecessor. It should be the in order predecessor. Predecessor as in the previous. Okay, predecessor. And if the right child is empty, then the PTR should be replaced with the PTR of left child should be replaced with the in order successor. In order successor. Okay. So left child should be replaced with the in order predecessor and right child should be replaced with the in order successor, predecessor and successor. Now with this, let us try to construct a threaded binary tree. See, let me take that same example that I had taken in the beginning. So the tree was something like this. A, B, C, D, E, and F. This was a tree. Now I'll try to do the threaded binary tree. First, do the linked representation as always. First part. Okay. Excuse me. So this is A. Its left child. B. And its right child is C. Okay. C. B's left child. It's not empty. So, yeah. I will write D here. And here it will be E. And here it is going to be F. Okay. So, this is how you'll construct the linked representation, right? Now, once you do this, now we will do the threaded binary tree. See here, okay, this is not empty, right? This is filled with B. This contains the address of C. Likewise, this is also not empty. This is also not empty. This is also not empty. This one is empty. This is empty. Let me represent the empty ones using red color. Okay. So this is empty, right? This is also empty. This is empty, null. This is also empty as in null. Here also empty. And here also. Now, you have to use these two conditions. Okay. But before that, let me write the in-order traversal of this tree. In-order traversal. In-order traversal. So if you remember, in-order is left child, root, and the right child. Left, root, and right child. So it would be D, B, E, A, D, B, A, E, A, F, and C. This is the in-order traversal. Now, what you have to do is you have to look at the empty or the null node. See here, the right child of the C. See, C is right child is empty, right? So here it says if the right child is empty, then replace it with the in-order successor. In-order successor. So what you have to do is see E is here and its successor is A. Its successor is A. So what you have to do is you have to take the connection from this empty node and make it point at A like this. What is this? Okay. Oh my God. Okay. 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 What just happened here? I don't know. Okay. Anyway. So here. Next is this one. Okay. D's left child is empty. D's left child is empty. If the left child is empty, then you have to replace it with the in order predecessor. See, D is a node that is empty. Its left side is null. So what you have to do is you have to start from here like this, draw that dotted lines and connect it to nothing. Okay, for now, like this. Likewise, B is right child. D is right child. Sorry. D is right, that is a successor. Okay, so this will now connect to B. Okay, and E is left predecessor. E is left is B. So again, from here, you will have a connection to this part. And E successor is A. E successor is A. So lines will connect in this manner. Okay. Likewise, let's do F. Okay. F's predecessor is A. So you'll connect it over here. And F's successor is C. Like this. And I have made this, but can you identify one small mistake that I have made in these connections? If you have understood, can you identify one small correction that I have to do? The correction is over this node. Can you tell me why? The correction is because C's right child is empty, so you will have to write the successor. But if you see C has no successor, right? So C would connect to nothing. So this is how you will do the threaded binary tree. Now let me do one more example so that it becomes clear. So A, B, C, E, and G. This is my tree. Okay, let me do the in-order traversal for this one first. So the in-order for this is, it is left, followed by root, then the right child. So left, okay. So first it is C, then B, then G, then E, then A. Okay. Now, how do I construct the threaded binary tree? So what I will do, I'll do the linked representation first. So this is A. A's left child is A's left child is B. B's left child is C, and B's right child is E, and E's left child is G. Okay. Now identify the empty nodes. I'll write here. So this is empty. This is empty. This is empty. This one is empty, and these two are empty. Now what you have to do is you have to draw the, see for A is here. It does not have any right child, so it has to be a successor, but there is no successor here. So what I will do is I will connect it like this. Likewise, while coming to C also does not have any predecessor for the left child. So this also will go like this. But C does have a successor. So right child, what is the successor of C? Successor of C is B. So right child will connect to B. Likewise, E. What is the successor of E? E is A. So from here, it would be to A. Likewise, G. G's predecessor is B. B. And G's successor is E. Like this. Okay. So, are you able to understand how to construct a normal threaded binary tree? Okay. Now, you take one tree and you try to draw the threaded binary tree for this. You draw the threaded binary tree for this. Okay. Now, let us see this one. Okay. See, the thing is, this is a threaded binary tree that you have. Threaded binary tree. Look very carefully. There are some normal links also, right? This, see, for example, if I consider this particular tree over here, see, this is a normal link, right? And this is a threaded link because it is, shown with the dots. So normal connections are shown with the actual lines, and also threads are shown using the dotted lines. Same, while you write the logic also, the threaded link should be shown differently as compared to the normal links that you have. Okay, so remember this when you're trying to write the threaded binary tree, the node for a threaded binary tree. The idea is, if there is a threads present, then the threads has to be distinguished from the normal link. That is how you have to write the code. Now, what we will do is we will write the code so that we can differentiate normal link and also the threaded link. See, next part is your node definition. Node definition. I will be using structure for this, and see, it is type def. I'll be using type def for this. So instead of having struct thread tree, struct thread tree, I will be using the name thread pointer. Thread pointer. Okay. Uh, okay. I will give that name. So I told you threaded link has to be separated from the normal link. So I will show it like this. Short int left thread. Then the normal link. Data type is thread pointer. So thread pointer left child. Then you have the normal data part. I'll assume the data is of the type character. So I'll write like this. If you don't want to specify it like that, you can also write it as just data type. Okay. Then again, for the right child, I'll show this is for the valid. Okay. So thread pointer, right child, and its thread. I'll close it. Okay. So this is for your normal. This is for your thread. Sorry, these are for your normal links, and this is for your data. Now the thing is, see here. Now what happens to the node is node also will slightly change. Node will slightly change. See, data part will be here anyways. Then data part will be in the middle. Okay. Then towards its left and right, I will make the change. So here and here, this will be the left child, your normal link. Okay. Left child, and this would be a right child. And I will show the thread over here. This would be the left thread, and I'll show this as a right thread. Okay. Now the idea is, okay, if this has a normal proper, it is pointing to a proper location. Okay. Then, okay, if it is true or if it contains a particular value, okay. Otherwise, this will, if it is, if this is not, if this is not having any value, then this would become, uh, this would become, if this is having a value, this would become what? This is true, so this would become false. This would become false. Whereas, see here, let me show you this. If this is not pointing to a valid location, then I would make use of left thread, right? So then this will become true. So left thread and right thread can have only values of the type true or false. Okay, true or false. So this is the reason why this particular statement that I have given the data type as short int because it will store only true or false type of value. Okay. So it can be either true or false. Now you have to remember a node is having 5 parts. Okay. One is data part, two parts for the left child, right child, and 2 parts for the pointers, threads, left thread and right thread. Now with this, we will try to now draw the trick. I'll use the same example. Okay. So before that, let me show you the thread. I'll show the thread formation again. A thread node. Okay. Now the node looks like this. See, it is going to have 5 parts. like this. Okay, so this is data, this is data, this is left child, this is right child, left child, right child, right thread, right thread, and this is your left thread. Okay, now assume two things. One thing is, if your right child was pointing to the valid location, that means it had a, if this particular node has a right child, then this would be true, right? So then this part, your right child, right thread part will be false. Correct? This part is going to be false. Likewise, if this is not pointing to a valid location, that means thread will be present. So this is going to be true. Remember this? With the help of this, let us try to draw the threaded binary tree. I'll take the first tree itself, that is A, B, C, D, E, and F. I'll try the threaded binary tree. So, what I will do is, I will first take this node A. I'll divide this into 5 parts. Okay, A will come here, the data part. This is my main node, right? So what I will do is I will store the information of this in a node called as root node. That also will have 5 parts. This is called as the root node. Okay, this will contain the information. So it will be pointing at the first node, that is your root node. So it does not have any data part. Okay, now understand that this is the left child, this is the right child. Okay, now check whether A is having a valid left child. It is having a left child, right? So it will point at its left child, that is B. So that also will have 5 parts. Likewise, A is right child. So it is like this: 1, 2, 3, 4, and 5. So B will be here and C will be here. Now the thing is, because A's left child is pointing to, it has a node after it. So this part will become false because it is not pointing, it is not used for pointing, right? Likewise, this also will become false. Are you clear? Okay. Now this root nodes left, this one and this one. So it is pointing at this node, right? A. So that is why this is false. But look at this one, the root node's right thread. So right child is not pointing at a valid location. So this becomes true. Now thread will come into picture. How do you draw? Directly from here to here itself. Okay. Likewise, B and for C. Let us try to draw for B. So B is pointing at the valid location. So 1, 2, 3, 4, 5. This is C. And here it is pointing at E. 1, 2, 3, 4, and 5. E. Okay. Now, what about its left child and right child? See, B is left child and right child. See, B is having a valid left and right child's, right? It is having, so this will be false. This also will be false. Correct? Whereas, what about C? Let us try to draw for C. C is having the valid left child. I'm not having the space, so I'll draw like this. But in your test, you try to draw it in the left side itself. So this is F, F. Okay, now let us try to figure out the threads. Let us start with C. If you see, C does not have any left child, C is not having any right child. So thread will become true. Thread will now become true. Now, if you remember, it's in order to traversal, it is B, D, B, A, F, and C. So you have to figure out C is for the this pointer, okay, this to the left. What you have to do is you have to identify the its in order predecessor. So C's in order predecessor is what? Predecessor is 1 minute, 1 minute. Um, so C, so this is D. Sorry, this should be D, right? This should be D. This should be D. Okay, so D is predecessor. D is not having any predecessor, right? So what we will do is we will connect this one to the root here, like this. What about D's right side? D is, does not have any right child, so it has to point at the thread. Which thread? Which is having after the after D, which value is present? B. So that is a successor, so it will point over here. Likewise for E, E's predecessor is B, and E successor is A. So we'll go like this, like this. So because it is not pointing, so thread will now become true. Okay. Similarly for F, there is no right, left and right side, so thread will become true. F, what is the for the F? What is the predecessor you have? For the F, the predecessor is A. So F, the left child will point at A, like this. What is the successor of F? C. And what is the successor of C? C is not having any successor, so it will point at the root itself. Root itself, like this. Are you understanding? This is how it is done. Let me do for a 4-node tree. Okay. So S, T, U, and V. So first I'll write S. This is S, and this is a root node. Okay, this is a root node. So S is left child. It's pointing at T. So 1, 2, 3, 4, and 5. This is T. S is right child is pointing at U. This is U. U is having a left child called as V. 5. So this is V. Okay. Now root left child is pointing at the main node. So S here. So because it is pointing, this value is going to be false. Whereas this one is not pointing, so it has to come here, and this would become true. Okay. No, it is not going to be true. This is also going to be false itself. Now, what about here in S? S is having the valid child, left child. So this is becoming false, false. And S's right child is a valid value. So this also is false. And here So T does not have any left child, so this is going to become true. Thread will become true now. So right child is also not having any values. Thread will become true. And U left child is present, so thread will become false. And this side, the right child is not present for U, so this is going to be true. And here, both of them will be true itself. Now, if I have to write the in order traversal for this one, then it would be T, S, V, and U. T, S, V, and U. Okay, so T is I have to write for T. Okay, so T's predecessor is nothing. So I will have to point at the root. Point at the root. T's successor is S. You have to draw the dotted lines like this. Likewise for U, U's right part is not there. So this will now point at the root. V's predecessor is S. And V's successor is U. Like this. So this is how you will write it. Threaded binary tree. In the test also, if they ask, you are supposed to draw this one. Okay. Now I'll give you one example problem you can do for this again. Threaded binary tree. Can you do the threaded binary for this one? Where each node has a clear representation of the data part, the left child, the right child, and also the left thread as well as the right thread. Okay. Now we will look at the traversal. So it says the in-order traversal of the threaded binary tree. Now you have a threaded binary tree. Now you will have to do the traversal of this in-order traversal. Okay. Now you see this. The function is in-order successor. The main I will be taking a node called as tree. Okay, it will assume that it is the main node, the top node, root node sort of. Okay, and the data type is threaded pointer because previously when I defined the node, that is how I have given the type def declaration of it. Now, see here, what I have to do is, for example, if this is a tree. Okay, so A, B, C, and D. What I will do is, see here, this one clearly says the way the in-order traversal works. For any node PTR in the threaded binary tree, we'll take this as PTR now. For any node PTR in a threaded binary tree, if the right thread is true, what does this mean by right thread is true? When does right thread becomes true? When there is no when there is no right child to it. Correct? When there is no right child to it. So, when the right thread is true, okay, the in-order successor of PTR is PTR of right child. So, if you remember, when there were no when there were no valid location, then we would use the thread and we would make it point to the successor, right? Okay. Otherwise, what we do is, okay, otherwise, if there is a valid location, if means if the thread is right thread is false, okay, then we go to the left. Okay, see here. Otherwise, we obtain the in-order successor of PTR by following the path of left child from the right child of PTR until we reach the node with left thread is equal to true. See how this works. Let me show you. First, we take temp of right child and tree of right child and make it as temp. Okay, so let me take this one. Does it have this right child? It does have a right child, so thread becomes false. Correct? So the right thread is false. Right thread is false. Then it is pointing at the valid location. So what you have to do? Then you have to come back to the left position here, left. Okay. And what you have to do is, uh, if the temp is not equal to left thread, okay, this part, if temp is not equal to left thread, then you have to go back to its left child here, like this. So let me show you how this works here. See, if there is a node, say like this, A, B, C, and D. I'll take this node. This is tree, so this itself is temp. Then on this temp, I will find this in order successor. If that is a node, then we come to the, if that is itself the tree, then we come to the break statement. Otherwise, what we will do is we'll go to the next node and display its temp. Okay, so this is how it works. So you don't really have this part, this threaded, inserting the node into the threaded binary tree. If you want, you can watch this, or else um, what you can do is you can refer this yourself. This inserting the node into a third threaded binary tree. That's all for the topic of threaded binary trees. You should know how to, you should know what is a threaded binary tree, what are the nodes in a threaded binary tree, what is called as a ref thread, how to do the right thread in a node. If there is a thread, then how to do the node formation, how to draw the tree with the threads in it. And you should also know the traversal. Okay, that's it for this video.